Hi, so I'm Susmita Adhikari. I'm a postdoc at UC-HiPACC. So I'll be giving a brief review of the recent developments in theory and measurement of the splashback radius in galaxy clusters. Right. So to begin with, we know that dark matter halos are basically the endpoints of all structure formation. That's where all the interesting galaxy and all the baryonic physics takes place. However, the boundaries of a halo, the actual physical boundary or what we define as a halo, is somewhat murkily described, right? In general, it's defined by some sort of a reference density, the radius at which the enclosed density reaches some factor of, say, the background matter density or the critical density. However, there is actually a physical way in which you could go ahead and define the boundary of a halo, which is what the splashback radius relates to. So the splashback radius, in the most general sense, is basically the radius at which the most recently accreted matter is turning around for the first time. So the matter has been accreted into the halo and it has reached its first apocenter in its orbit, which is shown over here, and it's turning around. And basically beyond this, you don't have any more matter which has been inside the halo, right? So, and this radius is actually accessible given the density profile of halos, the way we measure it, the way we conventionally think of it. As was shown in this 2014 paper by Benedikt Diemer and Andrei Kravtsov, where in the top panel we have the density profile of a dark matter halo. This is actually a stacked profile of dark matter halos, and in the bottom plot, what we're plotting is the slope of the density profile versus the radius scaled by the virial radius. And what they found is that the density profile of the halo becomes very steep in a very narrow localized region near the outskirts of the halo. In fact, it can become much steeper than what we conventionally think that NFW profile should be asymptoting to. Further, this has stopped working. Does anyone know what's happening? Okay. Oh, yeah, that's it. Yeah, but it's not working. Okay. Maybe I'll just use this. Right. So further, when we take the slope of the density profile and look at the corresponding location at the minimum of the slope with where it corresponds to in the phase space of the density of the dark matter halo, we see that the minimum of the slope actually corresponds exactly to the phase space boundary of the multi-streaming region of the halo and the infall region of the halo. So this is just the radial velocity versus the radius, and this is what we call the virialized region, and this minimum of the slope corresponds exactly to this, to basically where you can separate the phase space boundary. This also actually corresponds to the outermost caustic, which has been seen several times in self-similar solutions, in idealized solutions of dark matter halos, and sometimes you can also see a second dip in the density profile, which actually corresponds to the second caustic or the second turnaround radius of objects inside the halo. So the splashback radius basically corresponds to basically I like to think about it as the physical boundary of the halo. Naturally, when we look at the nitty-gritties in the details of the dark matter simulations, we find that halos are obviously not spherical objects. The splashback or the caustic shell itself can be aspherical, can be different along filaments and along voids, and a lot of intense work has been going into characterizing this feature and understanding this feature in details by Phil Mansfield at Chicago and also Benedikt Diemer, who has been trying to measure splashback radius by measuring these particle orbits in simulations. However, in a spherically average sense, in the simplest way, the main features that we find that the splashback radius follows is that it is largely a function of the accretion rate of the halo. So the faster the halo is growing, the smaller is the accretion rate. It is also a function of when scaled by the background matter density, it is also a function of when the halo formed, or rather the redshift at which the halo formed, which basically tells you how the background universe was expanding, and relatively the location of splashback could change. And also, not only in particles, you expect to see the splashback radius in massive substructure, which falls into dark matter halos. They similarly follow orbital motion inside of halos. And depending on the mass of how large your subhalo is, you expect the splashback radius to change just because during a subhalo's orbit, it loses energy in dynamical friction. So the most massive subhalos tend to splash back at a smaller radius than the least massive ones, which agree with particles. Right. So this can also be used as a probe for dynamical friction in halos. Also, I won't be going into it, but since the physics that goes into it is very simple, it's just gravity in an expanding universe, we also find that it can be sensitive to cosmology. Right. So recently, a lot of effort has been put into measuring this feature and actually finding this feature, going out and looking at galaxy clusters where you expect this feature to be the strongest, and trying to measure it in data. It was first done by Surud Moore in 2016, where he looked at red mapper clusters. So these are clusters which are selected based on the overdensity of red galaxies in the sky. So they tried to measure the splashback radius in the number density profile of galaxies around these massive clusters. So these clusters had a mass of greater than 10 to the 14. They were in the richness range of 20 to 100. And Surud measured it in SDSS. And then further, Chiwei Chang and Eric Baxter et al., they measured it in the DES data. So red map across DES galaxies and red map across SDSS galaxies. In Chang et al. 2017, they extend this measurement to include lensing. So they also measured the lensing profile around galaxy clusters to see this, to see the splashback radius. And the main takeaway from the papers is that when compared with simulations, it appears that the location of the feature is actually about 20% too small from your expectations. So the feature, both in the galaxy number density profile and in the lensing profile, is small by about 20%. The top panel, the black curve basically shows your measurement of DES clusters, and the red and green curve show the measurements from subhalos in dark matter simulations. And in the bottom panel, the black curve shows the measurement from simulations, and the red curve shows the measurement basically from DES data. And as you can see, that the minimum is about 20% away from where you would expect it from simulations. It was pointed out, right, and the other thing also worth noting is that we don't see any, for these massive clusters, even though in simulations we would expect to see some evolution of the feature with basically subhalo mass or galaxy magnitude. That is, you would expect to see a shift in the splashback radius if you select galaxies based on their magnitude, but there is no real evidence for dynamical friction, at least for these very massive clusters. Right. So going further, it was pointed out in a paper by Bush and White in 2017 that the location of the splashback feature can actually be very sensitive to the way in which optical clusters are defined. So the optical clusters were selected based on this parameter called richness, which is basically the number of red galaxies inside some given aperture. And this aperture, and so you're basically setting an aperture to define your richness, and then and you set this aperture on the tracers that you're going to use to measure the splashback radius. So Bush and White were worried that you are probably artificially introducing a feature at the location of this aperture, which is actually supposed to be very close to the splashback radius. So when you change the size of the aperture, there was some movement in the splashback feature, which was worrying. So we're currently trying to disentangle this effect and see in mocks of red mapper to see where that goes. But alternatively, the other approach that we have taken is to change our method of cluster selection. So instead of using red mapper or optically selected clusters, we can also, there's a lot of data in which clusters are selected in different ways. Like, for example, we're taking the SZ selected clusters, which are selected by a decrement in the temperature in CMB maps, and they're recognized as shadows in the CMB maps. So there are about, there's a large sample, there's a fairly decent sample of SC selected clusters. These have been selected, this is a completely independent method of selection, and it does not have to do anything with the actual tracers that we are going to use to measure the splashback radius, that is the galaxies or basically the mass distribution. We have about 300 clusters in the DES footprint. So we are doing SZ clusters cross DES galaxies again. And the mean mass of these clusters is somewhat higher. It's about 410 to the 14. M500 is 410 to the 14 M sun. And the mean redshift is also higher than what we had previously looked at. So right now we're doing these measurements. And so far, these are very preliminary results. So far, what we find that when we take the SZ clusters, the main measurement is in the bottom panel. The red curve is the SZ measurement. The black curve is the measurement from simulations from a stack of clusters with the same mean mass. And the blue curve is the same measurement for subhalos of a given abundance match to these galaxies. And what we find is that largely in the SPT sample, that the splashback radius is more or less consistent with what we expect from simulations. From the particle, the location of this feature is more or less consistent. Another thing just interesting to note is that the inner profiles actually follow the particle of galaxies, of the galaxy distribution around clusters actually follows much more closely with the particles than subhalos. In simulations, that is sort of expected because there's a lot of tidal stripping and artificial disruption going on, but it's still encouraging to see that they kind of agree well with the particles in the inner regions. But the upshot is that the splashback radius is more or less consistent in these SPT clusters. When we do a lambda cut, richness cut in the red mapper sample to basically mean mass match to SPT, we still find a much smaller splashback radius in the red mapper clusters, and much smaller than simulations as well. And this is something we have some ideas as to what could be going on, but we don't have definitive answer yet, and we're still working on it. So right, so basically to summarize that this tension still exists. We cannot reconcile the red mapper splashback measurement to the SPT measurement. Right. So, and finally, I would like to take a short deviation apart from just measuring the splashback radius, what it can tell us, and especially since this is a galaxy workshop, what it can actually tell us about galaxy evolution. So as everyone here knows that in cluster environments, the density of red galaxies is much higher than in fields. So why the splashback radius is basically interesting is because it sort of gives you a clock, right? So if you have a population of halos that shows a splashback feature, it basically tells you that some part of that population of halo has at least completed one pericentric passage and reached first turnaround, right? So for example, if I just take a simulation and I just plot the phase space of objects that are on infall or that have been accreted, say, after A of 0.8, this is the infall stream, and I get this black curve which does not basically show a really strong splashback feature. It's more or less consistent with being infall. Whereas if I take things which have been accreted long back and have stayed in the cluster for a long time, they have the strong clustered component, and you start to see these splashback features. So what we're trying to do is trying to use splashback as a clock. what we do in observations is split galaxies based on their colors, and we try to see whether or not we see a splashback in that sample of galaxies. So if you just sub-select the reddest galaxies in a cluster, you see a very strong feature. And as in, also when we take the Green Valley galaxies, we also see somewhat a splashback feature, which is here. However, when we take blue galaxies, this feature tends to go away. Sorry. This feature tends to go away, and we don't see any significant dip in the density profile of these galaxies. So depending on at what color you start to lose this signal, you can say how much quenching has taken place in, say, an orbital time scale. So with that, I'll finish, and I'll just leave up the conclusions. For now, in SPD clusters, we see a largely consistent measurement. We can use the splashback radius to try to constrain quenching models, and yeah. Thank you.
Thank you very much.
So this is beautiful work. I especially like your clock idea. Let me make a crazy, wild suggestion. Many years ago, in a paper that we published back in 1991, Lahav, Lilly, me, and Martin Rees, we first worked out the caustic structure around clusters as a function of the cosmological constant. And basically what we found was exactly the sort of thing that you're seeing when you use the red mappers, at least. Namely, the effect of a cosmological constant is to push the caustics further out.
I see.
So here's the radical idea. This is actually a test of the nature of the dark energy versus some kind of modified gravity. As you know, modified gravity is an alternative explanation for the observations of the apparent accelerated expansion of the universe, but it would have a very different effect on the caustic structure. Now, I realize, depending on what data set you use and how you analyze it, it's changing this difference between, but were you aware that this is actually a test of the nature of dark energy versus some alternative modified gravity? And if not, maybe you should look into that.
Yeah, I published a paper just 2 weeks back exactly on that topic.
Okay, so what were your conclusions?
So what I found was that in certain models of modified gravity, like I looked at FFR and DGP, and we found especially that in subhalos, like in the number density profile, the main conclusion was that the effect of dynamical friction sort of slows down in modified gravity, so things splash back to a larger radius than what you would expect in lambda CDM. So that was the main conclusion. So it's a mass-dependent effect. It's quite significant. You can get as large as 15% differences. But statistically, we can actually do quite well in the measurements already. But systematically, we still need to figure out these, like, how do we interpret, these differences? So yeah, so there is definitely some signal there. Thanks.
So let's thank Susmita again and all the speakers of the afternoon.